Welcome to this explainer. Look, if you're a focused learner trying to figure out what mechanical engineers actually do day in and day out, you're in the exact right place. Today, we're going to explore how mechanical engineering literally shapes the world around us. We'll be breaking down the complex processes, the universal languages they use, and the absolutely critical responsibilities that define the profession.
Okay, let's jump right in. To really get mechanical engineering, we first have to look at the sheer scale of it all. We're talking about designing crazy complex satellites that are built to survive and operate in the harsh, unforgiving vacuum of space.
But it's not all off-planet. It's also down here, developing those ultra-precise, high-speed rail networks that safely move literally millions of people across continents every single day. And it's engineering incredibly robust aerospace landing gear. Think about the immense forces those components have to absorb just to get an aircraft safely back on the Earth. It's wild.
So here's our game plan for this module. We're going to cover the scope of engineering, the language of design, quality and problem solving, ethics and safety, and we'll wrap the whole thing up with a pretty sobering case study on 3 Mile Island.
All right, kicking things off with Section 1, the scope of engineering, designing the world. You'll often hear mechanical engineering called the broadest engineering discipline, and there's a good reason for that. It intersects with practically every global industry. These engineers operate in some seriously intense and demanding environments. Take the energy sector, for example. Designing an offshore drilling platform means you're battling massive ocean forces, highly corrosive saltwater, and really complex fluid systems. Out there, reliable design isn't just a nice-to-have, it is absolutely crucial to prevent a total disaster.
Moving right along to Section 2, the language of design, GD&T standards.
So how do teams actually communicate these massive global projects before a single piece of metal is ever cut? Well, they use an amazingly precise language called geometric dimensioning and tolerancing, or GD&T for short. By establishing really strict, uniform practices for drawing and interpreting designs, GD&T is basically the bridge between a brilliant idea and a successfully manufactured product. It makes sure the designer, the machinist, and the quality inspector are all reading from the exact same playbook.
Now, what's kind of fascinating is how this language changes depending on where you are in the world. We've got two main players. First, the American approach, ASME Y14.5. This one conveniently rolls all the theory and part dimensioning practices into one single document. But then you have the international system, ISO GPS, which spreads everything out. If you wanted to buy the basic specs for ISO, you're buying multiple documents, like ISO 8015, 1101, and 2768. And honestly, combining all those can end up costing you a whole lot more. To give you a taste of how this works, let's look at one of the biggest technical rules in GD&T. Rule number 1, which is also known as the envelope principle. Imagine a simple shaft. This rule basically says that the dimensional tolerance actually limits how much the part's shape can deviate. So, in plain English, if you make this shaft to its absolute maximum allowable size, it has to be perfectly cylindrical from end to end. No bending, no warping. This is exactly how engineers mathematically guarantee that parts will actually fit together in the real world. Which brings us to Section 3, quality and problem solving. What happens when things go wrong? Because, let's face it, a perfect drawing on a computer screen is one thing, but the messy reality of the manufacturing floor is a whole different ballgame. When things go sideways during production, quality professionals and engineers don't just guess at solutions, they lean on highly structured problem-solving frameworks. Two heavy hitters you'll see a lot are PDCA, which stands for Plan, Do, Check, Act, and DMAIC, representing Define, Measure, Analyze, Improve, and Control. These aren't just corporate buzzwords, guys. They are rigorous methodologies for continuous improvement. And to make those frameworks actually work, engineers use specific, hands-on analytical tools. If a part keeps failing on an assembly line, an engineer might map it out with a fishbone diagram, or use the 5 whys to drill down way past the surface symptoms. They use Pareto charts to spot the most frequent defects and process mapping to hunt down hidden inefficiencies. The ultimate goal is always to find the true, underlying root cause, rather than just slapping a Band-Aid on a symptom. All right, Section 4, ethics and safety, the weight of responsibility. This right here is what I consider the absolute climax of the engineering lifecycle, the ethical burden. All the technical skill in the world means nothing if it isn't guided by a commitment to protecting public safety.
The American Society of Mechanical Engineers actually highlights this constant intense friction between market pressure, management wanting things done faster, and an engineer's ethical duty. People will always push for shorter timelines, but here's the crucial point. The engineer must be the one to stand firm, take the necessary time, and guarantee the product is completely safe. At the end of the day, the accountability rests entirely on their shoulders.
Let's look at a real-world example in Section 5, the case study on 3 Mile Island. To really grasp that ethical weight we just talked about, history gives us a pretty stark reminder. Let's set the scene. The 3 Mile Island nuclear plant. This was a massive piece of energy infrastructure that relied on a highly complex pressurized water reactor, or PWR, system. On March 28, 1979, the unthinkable actually happened, a partial meltdown of the Unit 2 reactor core. Now, purely from a structural engineering perspective, the containment system actually did its job. It proved effective, resulting in minimal direct health impacts to the public. But the broader picture? Absolutely catastrophic. The psychological shock and the economic fallout completely reshaped the global energy industry forever. So, what did the engineering community actually learn from 3 Mile Island? Well, the disaster definitely exposed some severe technical flaws in the reactor's design. But honestly, more importantly, it highlighted the incredibly critical relationship between engineering and operational management. It proved that massive failures are almost never just a broken valve or a technical glitch. They are a total breakdown of human and operational factors. It was a massive wake-up call, emphasizing the urgent need for engineers to anticipate failure modes and integrate human factors into their designs right from the very beginning. Okay, let's bring it all home with our module summary and key takeaways. Let's quickly synthesize what we've covered today. We started with the massive scope of mechanical engineering and how it drives huge global industries like aerospace and energy. We talked about GD&T, the universal language of design, and looked at the differences between ASME and ISO standards. We explored how structured frameworks like DMIAC are absolute lifesavers for solving complex manufacturing problems. And finally, we saw that above all the math and the blueprints, an engineer's ethical responsibility to safeguard the public absolutely must supersede production speed. So, I want to leave you with one final vital question to chew on. As you move forward in your education or step out onto the actual production floor, you are absolutely going to face intense pressure to work faster. When that moment comes, how will you ensure that safety and human factors are never compromised in your designs? Give that some serious critical thought as you prepare for your future. Thank you so much for joining me for this explainer, and keep learning.